Okay, in part 3, what we're going to try to do is to finish the problem by looking at the intercepts, looking at the limits, and then fixing our sketch of our graph. Now, I rewrote our function in terms of a fraction. It works better that way. How do we find intercepts? We set x equals 0 first. Well, when I set x equals 0, I get y equals 0. So I get one thing that looks like this. So it has at least one intercept. How do I find the y-intercept? I find the y-intercept by setting this whole thing equal to 0. Well, a fraction is only 0 when the top is 0. So the fraction is only 0 when x equals 0, and we already have that. So it really only has one intercept. That's number 1. Number 2, we want end behavior. What's happening way to the right and what's happening way to the left. I think left is actually easier, so we're going to do that. I'm going to say lim x arrow minus infinity. You'd think I'd want this one, but I don't. I want this one. And you'll see why in just a second. I want to use the easiest one. Now, we can't plug in infinity or negative infinity, but we can't argue, right? When x is a very large negative number, this is a very large negative number. When x is a large negative number, the exponent is very large positive. E to a very large positive is a very large positive. And so I get something like minus infinity times infinity. Now, that's not an indeterminate form, right? That's large times large, that's negative. That says way to the left. That graph is going way down. Now let's do way to the right. Way to the right. For way to the right, I'm going to use the other way of writing the function. You'll see why in just a second. When you've done about 10 of these, this is really easy. Here we go. Now, why did I pick this one? Well, when x is big positive, the top is big positive. When x is big positive, the bottom's big positive because a is a constant thing. So this is L'Hopital's rule. So then I write down L'Hopital's rule. How's L'Hopital's rule work? You take the derivative of the top, you take the derivative of the bottom, this, right? And then you take the limit all over again. Well, now the top is just 1, the bottom's getting huge, and we can see that way to the right, the limit's 0. Way to the left, the limit's negative infinity, and it only has one intercept. So what I'm going to do is go to our graph and fix our graph with these two things. Remember, our graph looked like something like this. I had it going up like this and down like this. Now, what's wrong with that? Well, first off, there's only one intercept, and it was at 0, 0. So I needed to have at least started it like that. And it's supposed to be concave down. Let's see if I can't make that just a little bit better. Good. Now, 1 over a, we didn't do anything wrong with 1 over a. Yes, the function hits a peak. At 2 over a, we know it changes concavity, but the problem is there's only one intercept. It can't cross again, right? So whatever this does, it has to come down like this. And I know way to the right, the limit was 0. So I get something that's like this. And there's our perfectly fixed graph. And by the way, they do use these in probability and statistics. It's not a normal bell curve. It's the sort of curve that they used when they're trying to study the percentage of appliances that last a certain amount of time. Which means this is the one, for example, that gets used in industry an awful lot. Anyways, there's our graph.